Welcome to our last video together here in college algebra this semester. I'm glad that you've stuck with it and made it to this point. There's not a lot of students that are able to push forward to this point, and so I admire you for sticking through things and putting in the time that's been needed to do this. I'd like to take a look here at the binomial theorem and what it's actually used for, and we're only going to take a look at a couple applications actually of it. There are many things that the binomial theorem is good for. One of the most basic is to look at a binomial like this, a plus b to a quantity, and we need to expand that, and of course that's a little job to do if this exponent is small. It doesn't really take long even to expand a plus b to the fourth power, but when we get something like a plus b to the seventh or the eighth, something like that, things get a little bit tricky. Now, there are some things that we can note here. Trying to expand a plus b to the n will always bring about n plus 1 terms. So in other words, we've got a plus b to the second power, that brings out 3 terms. A plus b to the third power brings out 4 terms. As we proceed from any term to the next, the power of a decreases by 1 and b increases. So you notice here a goes from 2 to 1, 3 to 2 to 1 to 0, 4, 3, 2, 1, a to the 0. And for each term, the sum of the exponents, well, first of all, the power of the b increases, b to the 0, b to the 1, b to the 2, b to the 3. And the other thing here, for each term, the sum of the exponents of a and b has to equal n. It's always a case in each term has the form c, a to the n minus k, b to the k, where the coefficient c is an integer and k goes from 1 to n. So the following formula is true for each of the first n terms of expansion. And you can kind of get a feel here for what's happening if it's a plus b to the fifth, a to the 5, 4, 3, 2, 1. On the other hand, we have b to the 0, 1, b to the 2, b to the 3, b to the 4. Okay? And so we can kind of get a pattern also for the coefficient here of the next leading term. 1 times 5 over 1, 5 times 5, or 5 times 4 over 2, etc. We're going to see how that plays out for us here in just a little bit. Let's consider a plus b to the n for an arbitrary positive integer n. The first term is a to the n with a coefficient of 1, and you'll notice the pattern here. We're counting down 1 times n times n minus 1, n times n minus 1 times n minus 2, n times n minus 1 minus 2 minus 3. And so notice what we're doing. If the number of the term is the fourth term, then what we've got is 3 different factors here on top and then 3, 2, 1 on the bottom. And in fact, in general, the coefficient of the k plus 1 term of the expansion is n times n minus 1, n minus 2, n minus 3, all the way down to n minus k plus 1. Now, this little result here brings us to a notation that some of you may have seen in the past. Most of you probably have not. It's called factorial notation. And if we have n factorial, we take n times n minus 1 times n minus 2 all the way down to 1. N has to be greater than 0. 0 factorial is just 1. So some examples here. If we have 10 factorial, 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. If we have 3 factorial, we're looking at 3 times 2 times 1. If we've got n minus 1 factorial, look what we've got here. We start with n minus 1, and then 1 less than n minus 1 is n minus 2. N minus 3, n minus 4, all the way down to 3 times 2 times 1. And so as we look at that, that is our meaning of factorial. And we need one more little piece of notation here. and this is the coefficient of the k plus 1 term of the expansion. In choose k. Notice that's C-H-O-O-S-E, in choose k. And we have to use our factorial here. So if we're looking at 8 factorial times 0 factorial, we're looking at 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 1, and this turns out to be 40,320. If we're looking here at 6 factorial divided by 3 factorial, 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. Those drop out and we are left with 120. Now if we get into our choose factorial, 7 choose 5, what we have here is 7 factorial divided by 5 factorial times 7 minus 5 factorial. And so 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1 times 2 times 1. Well, these guys drop, and then it's supposed to be a 1. 6 divided by 2 is 3. 7 times 3 is 21. Rewriting our next expression here so that it does not contain factorials, look at what we've got. We've got 2n plus 2 factorial over 2n factorial. Well, we're looking at 2n plus 2 times 2n plus 1 times 2n, etc. Now this is going to be 2n factorial over 2n factorial. You'll notice that those cancel, and we can write this as 2n plus 2 times 2n plus 1, or if we expand it out, 4n squared plus 2n plus 4n plus 2, which is 4n squared plus 6n plus 2. And I would accept either of those answers right there. So we're looking here to write that without factorials, and we managed to pull that off. Let's take a look here at our next one, and it probably looks very similar. 3n plus 1 factorial over 3n minus 1 factorial. So we've got, I always start with the bigger one, guys. 3n plus 1, subtract 1 from that, we've got 3n. Subtract 1 from that, we've got 3n minus 1, and I can leave that at 3n minus 1 factorial as I can the bottom. Gone and gone. And so we're left with 3n plus 1 times 3n, or 9n squared plus 3n. And I would accept either of those answers. And so now, the thing that you've all been waiting for, not just the last concept of the semester, but for the grand finale in the binomial theorem. We take a look here, we notice all of the things that we just talked about. The first term of an expansion is always that first term raised to the nth power. And then we start doing our choosing and our factorials. And so we've already looked at the characteristics that we have. We'll see above. We'll put a star by it. We'll come back up here and we'll put a star by it. We've already talked about the different characteristics that the terms have. And so now we'll just jump right in. Use the binomial theorem to expand and simplify. Guys, I'm going to take this from the start here. 4 choose 0, even though that's going to be 1. X to the 4th, y to the 0. Plus 4 choose 1. X to the, now this exponent on the x is going to go down. The exponent on the y comes up. I'm going to write the 1 here for emphasis. Plus 4 choose 2. x is raised to the second power, so is y. Notice these exponents should always add up to what our exponent is here in the binomial. Plus 4 choose 3, x to the 1, y to the 3. Plus 4 choose 4, x to the 0, y to the 4th this time. And again, we know that's going to be 1. So we simplify this, we get x to the 4th plus 4, x cubed y plus 6, x squared y squared plus 4, xy cubed plus y to the 4th. Alright. And then we take a look at 7 here, and guys, again, notice that we have a binomial raised to a power. And so let's take a look here at what we've got. We've got 5 choose 0, x to the negative 3 raised to the 5, negative 2x raised to the 0, plus 5 choose 1, x to the negative 3 raised to the 4, negative 2x raised to the 1, plus 5 choose 2, x to the negative 3 to the 3rd, negative 2x squared, plus 5 choose 3, x to the negative 3 to the second power, negative 2x to the 3rd, plus 5 choose 4, x to the negative 3 to the first power, negative 2x to the 4th power, plus 5 choose 5, x to the negative 3 to the 0, negative 2x to the 5. And so we can simplify this to x to the negative 15 minus 10 x to the negative 11 plus 40 x to the negative 7 minus 80 x to the negative 3 plus 80 x minus 32 x to the 5th. And of course, you guys know how I feel about negative exponents. Negative 1 over x to the 15 minus 10 over x to the 11 plus 40 over x to the 7 minus 80 over x cubed plus 80 over x minus 32, whoops, that's an 80 to the x power there, plus 80 to the x minus 32 x to the 5th. Okay, so we've used the binomial theorem to expand there. And then finally they want us to find the last 3 terms. Well, let's think about this now. The last 3 terms, okay? The last term, if we start, is going to be 12 choose 12, and we know that the back term, negative 2t, is going to be raised to the 12th power, and this will be raised to the 0. Alright, so we can kind of work backwards here. This is going to be 12 choose 11, s to the 1, negative 2t cubed to the 11, and this is going to be 12 choose 10, s to the 2nd, negative 2t cubed to the 10th. And so we expand that. As you might guess, we actually get a fairly big number here. This is equal to 67,584 s squared t to the 30 plus, oops, excuse me, we've got a minus here, minus 24,576 s t to the 33rd plus 4,096 t to the 36th. Okay, so again, if I need just the last three terms there, I'm going to start from the back. I know the last one's 12, choose 12. These exponents have to add to 12, and so this is a 12 and a 0. 12, you back it off, 11 and 1, 10 and 2. If we want the fourth term, okay, if we want the fourth term here, let's think about what our numbers are going to look like when we do the choosing. We know that we're going to start out with 10 choose 0, 10 choose 1, 10 choose 2, 10 choose 3. Well, that's going to be the coefficient on that fourth term. So we've got 10 choose 3. Alright, and then our first term here, 3x squared. Now, we know that that is going to be raised to the 10 minus 3, or the 7th power. Okay, we can always do the subtraction. Notice up here, 12 minus 10 is 2, 12 minus 11 is 1. And then these exponents have to add, so this is negative y cubed raised to the, well, 7, and this guy have to add up to 10. And this works out to be negative 120 times 3 to the 7th, x to the 14th, and then this is negative y to the 9. And when you multiply all this out, we get an overflow error on the calculator, so we'll just leave it at that. And my friends, when it comes to your college algebra videos for this semester, that's the end. It's been a pleasure doing them for you. I hope that you've been able to learn a little along the way. I realize this is a format that has required much more time on the front end, but I hope that you have found this to be a little easier way with the constant repetition and being able to go back and review. So, of course, if you have questions, bring them to class.